Nobody actually knows how big the universe is, not really, and not to the precision you would demand of almost anything else you trusted. We have two great ways of measuring it, two of the most careful measurements in the history of science, and they hand us two different answers. One says the universe is expanding at about 73, the other says about 67. The gap between them is roughly 9%, and here is the part that should stop you. It is not shrinking. For years, everyone assumed better telescopes would gently close it, the way better measurements always had before. Instead, the sharper our instruments have become, the wider and more stubborn the disagreement has grown. Two numbers, measuring the very same universe that simply will not shake hands, and whatever is hiding in the gap between them may turn out to be a piece of physics we have never seen. Get comfortable. If you enjoy the feeling of solid ground being quietly pulled out from under what you thought you knew, a slow like and subscribe helps this channel reach more curious minds like you. Because by the end of tonight, that tidy little number you have always been shown for the age and the size of the universe will never feel quite so certain again. Now, let's slowly settle into the dark. There is a single number that quietly decides how big the universe is. It does not look like much when you write it down. It is not a distance, or a mass, or a temperature. It is a rate, the speed at which space itself is stretching right now in every direction at once. The people who study this call it the Hubble constant, and they write it as the letter H with a small zero beside it, spoken aloud as H0. That modest little symbol is the closest thing all of cosmology has to a master key. Hand it to the equations and out comes the age of the universe, the width of the part we're able to see, and the way the whole thing ends. Change it, even slightly, and all three of those answers shift beneath your feet. For most of the last 100 years, measuring that number felt like a slow, satisfying climb towards certainty. Each generation of astronomers built better telescopes, gathered more light, and pinned the value down a little more tightly than the generation before. The error bars shrank, the confidence grew, and everyone assumed that if you measured carefully enough, from enough different directions, all the answers would eventually fold together into a single settled figure. That is how measurement is supposed to work. You circle the truth, and the circle gets smaller until you are standing on it. Except, that is not what happened. Instead, something strange crept in around the edges, and it has been growing quietly for years. There are two great methods for measuring how fast the universe is expanding. They are completely independent. They rely on different objects, different physics, different centuries of work. One reads the light of dying stars in the nearby universe. The other reads the faint afterglow of the beginning of time itself. And when you follow each method carefully, all the way to its answer, they hand you two different numbers. One method says the universe is expanding at about 73. The other says it is expanding at about 67. The units do not matter for now, only the gap between them, and the gap is roughly 9%. That may not sound like much. 9% is the difference between a good day and a slightly better one. But in a measurement this careful, 9% is a chasm. It is far, far larger than the uncertainty in either number. Picture two teams of surveyors measuring the height of the same mountain, each one certain to within a single footstep, and coming back with answers that differ by hundreds of meters. Somebody, somewhere, has to be missing something enormous. And the unsettling truth is that after decades of looking, nobody can find what it is. These two numbers refuse to shake hands. That is the phrase I want you to hold on to tonight, because we are going to come back to it more than once. Two numbers that should be the same, that describe the same universe, that were measured by some of the most careful people who have ever lived, and they simply will not meet. It is a 9% crack running right through the middle of our picture of the cosmos, and every time we look closer, the crack does not close. It widens. To feel why this matters, you have to understand what the Hubble constant actually is. When astronomers look out at distant galaxies, they notice something remarkable. Almost every galaxy is moving away from us, and the farther away a galaxy is, the faster it is fleeing. This is not because we are unpopular, or because we sit at some special center. It is because space itself is expanding everywhere, all at once, carrying the galaxies along with it, like markings drawn on the surface of a balloon that is slowly being inflated. The Hubble constant is simply the rate of that stretching. It tells you how much faster a galaxy recedes for every extra step of distance you put between it and yourself. The way physicists actually write the number is in kilometers per second per megaparsec. A megaparsec is a unit of distance, about 3.26 million light-years, which is a comfortable stride across the local neighborhood of galaxies. So a Hubble constant of 70 means that a galaxy 1 megaparsec away drifts from us at about 70 kilometers every second, and a galaxy 100 megaparsecs away drifts 100 times faster than that. It is a rule about how quickly the distances in the universe are growing. And because the expansion has been going on since the beginning, if you know how fast space is stretching now, you can run the film backward and ask when everything was crammed together into a single point. That backward calculation is where we get the age of the universe. It is where the famous figure of 13.8 billion years comes from. The width of the observable universe, that number you have heard, something like 93 billion light-years across, comes from the same place. Almost everything we say about the size and age of reality traces back to this one rate of expansion. So when two trustworthy methods disagree about that rate by 9%, they are not having a small technical squabble. They are disagreeing quietly about how old the universe is, about how big it is, about the size of the stage on which absolutely everything has ever happened. And that disagreement has a name now. Astronomers call it the Hubble tension. In the more honest moments, they have started calling it something stronger. They call it a crisis. The word crisis is not thrown around lightly by careful scientists. It gets used here because of a particular threshold, a line that physicists draw to separate an interesting coincidence from a real result. That line is called 5 sigma. Without getting lost in the mathematics, 5 sigma is the point at which the odds of a fluke drop to about 1 in 3.5 million. It is the same standard of proof that particle physicists demanded before they would announce that they had found the Higgs boson. It is the gold standard, the moment you're allowed to stop saying maybe and start saying yes. The disagreement between these two ways of measuring the universe has now climbed past that line. By the field's own strictest rule, the gap between the two numbers is not noise, it is real, and it should not be there. What makes it stranger still is the direction it has moved. In science, when two measurements disagree, the usual cure is patience. You gather more data, you sharpen your instruments, and the two answers slide toward each other until they meet in the middle. That is the reassuring rhythm of the whole enterprise. But this disagreement has done the opposite. As the telescopes improved and the error bars tightened, the two numbers did not drift together. They dug in. The better the measurements got, the more certain each side became of its own answer, and the more impossible it became to write the whole thing off as a mistake. Just recently, in the early part of this year, astronomers announced the most precise local measurement of the expansion rate ever made, tightening it to within about 1%, and the number came out to 73.5. Meanwhile, on the other side of the argument, the readings from the early universe have only doubled down near 67. 2 roads, 2 numbers, and the ground between them getting wider, not narrower, the harder anyone looks. I want to be careful and honest with you here, because this channel is not in the business of frightening you about the sky. There is nothing dangerous about this. The universe is not about to do anything to us. What is happening is subtler and, if you let it, stranger and more wonderful than any disaster. 2 of the most careful measurements humanity has ever attempted are calmly, stubbornly contradicting each other, and in that contradiction there is a hint, a whisper, that something about the universe is not what we have been assuming. Either a chain of measurements built up over an entire century hides a flaw that no one has been able to catch, or our best description of how the cosmos works is missing a piece. There is no comfortable third option left, and to understand how we ended up here, staring at 2 numbers that will not meet, you cannot start with the tension itself. You have to go back and build the whole thing from the ground up, the way it was actually built, one careful step at a time. Because each of these 2 numbers is the top of a long, patient tower of reasoning. On one side is a ladder, a real chain of measurements reaching from the ground beneath your feet, out to the farthest exploding stars. On the other side is a photograph of the universe when it was still an infant, taken in a light too faint for your eyes to see. Both towers are astonishing. Both were built by people who checked their work obsessively. And somewhere in the space between the 2, hidden in plain sight, is the reason the scale of the universe has quietly stopped making sense. Before we climb down to that first simple trick, it is worth sitting for a moment with how strange it is that the universe has a single expansion rate at all. There is no law written anywhere that says it had to be this tidy. The cosmos could have been a chaotic patchwork, stretching quickly in one direction and slowly in another, growing in fits and starts from one region to the next. Instead, on the larger scales, it appears to be almost perfectly even-handed. It expands at the same rate everywhere, in every direction, as far out as we can see. That evenness is itself one of the profound facts about our universe, and it is the reason a single number, the Hubble constant, can carry so much on its shoulders. One number, and it describes the growth of everything. So when that one number falls into doubt, the doubt does not stay politely contained. It seeps into every corner of the picture at once. Consider just how much rides on it. The age of the universe is essentially the expansion rate turned inside out. If space is stretching at a certain speed today, you can wind the film backward to find the moment when all the distances shrank to nothing, and that moment is the beginning. A faster expansion means the galaxies flew apart more quickly, which means they needed less time to reach the separations we see now, which means a younger universe. A slower rate means an older one. So the 9% disagreement between our two numbers is not an abstract quarrel about a decimal place. It is a disagreement about the age of everything, worth something on the order of 1 billion years, one way or the other. Two measurements of the same cosmos, quietly disagreeing about when time itself began, and the same is true of size. The farthest we can possibly see is set by how long light has been travelling toward us since the beginning, stretched along the way by the very expansion we are trying to pin down. Change the expansion rate, and you change the calculated distance to the edge of the observable universe. Change the age, change the size, change the entire scaffolding on which we hang every other cosmic fact. This is why astronomers care about this one number, with an intensity that can look, from the outside, wildly out of proportion. It is not one fact among many. It is the fact that all the others lean on. So let us begin the way the astronomers did, not at the edge of time, but close to home, with the oldest and simplest trick in the entire book. A trick you can perform right now, with nothing but your own two eyes. Hold up one finger at arm's length in front of your face. Close your left eye and look at your finger with only your right. Now switch. Close your right eye and open your left. Your finger appears to jump sideways against whatever is behind it. The far wall, the window, the trees outside. Nothing moved. Your finger stayed put. The background stayed put. The only thing that changed was your point of view, the small distance between your two eyes, and that little jump, that shift of a still object against a more distant backdrop, is the foundation stone of every measurement of cosmic distance ever made. Astronomers call it parallax, and it is the very first rung of what they call the cosmic distance ladder. I want you to keep that image of the ladder in your mind for the rest of the night, because it is going to matter enormously. Measuring the universe is not a single act. You cannot pull out one tape measure long enough to reach a distant galaxy. Instead, you measure something nearby using a method you trust completely, and then you use that nearby thing to calibrate a method that reaches a little farther, and then you use that to calibrate something farther still. Each method is a rung. Each rung is anchored to the one below it. And the whole structure, standing on the solid ground of simple geometry, is how humanity climbs from the Earth all the way out to the edge of the visible cosmos, rung by rung. If any rung is weak, everything above it wobbles. So the astronomers began at the bottom, with the sturdiest rung they could build, the one that assumes almost nothing. Parallax assumes nothing but the shape of a triangle. Here is how it works on the sky. The Earth travels around the Sun once a year, which means that in the summer we sit on one side of that orbit, and 6 months later, in the winter, we sit on the far side, about 300 million kilometers away from where we were. That distance between the two sides of Earth's orbit becomes the baseline of an enormous triangle, the same way the distance between your two eyes was the baseline for your jumping finger. If astronomers photograph a nearby star in the summer, and then again in the winter, that star appears to shift ever so slightly against the far more distant stars behind it. Measure the size of that shift, know the length of your baseline, and a little geometry hands you the distance to the star. No assumptions about what the star is made of, no guessing at how bright it truly is, just the angles of a triangle, the same mathematics a surveyor uses to measure the width of a river without getting wet. There is something deeply reassuring about this rung, and it is worth sitting with for a moment. Almost everything else we're going to talk about tonight involves an assumption of some kind, a belief that a certain kind of star behaves a certain way, a trust that the physics we see nearby also holds far away. Parallax is nearly free of all that, It is pure triangle. When a surveyor measures a triangle, you do not lie awake wondering whether the triangle might be lying to you. And for the closest stars, this is exactly how their distances are known, with a confidence that feels almost like touching them. But there is a catch, and the catch is the reason the ladder needs more than one rung. The farther away a star is, the smaller its parallax shift becomes. A nearby star swings noticeably from summer to winter. A star 10 times farther swings 10 times less. Push out far enough, and the shift becomes so tiny that it vanishes into the blur of the atmosphere and the imperfections of the instrument. For a very long time, this limited parallax to only the nearest handful of stars, a tiny bubble around our sun, a few hundred light years across at best. Beyond that bubble, the triangles became too thin to measure, and the method went blind. In our own era, we have pushed that bubble outward more than anyone in history thought possible, and the story of how is quietly one of the most beautiful in modern astronomy. A European spacecraft called Gaia spent years perched out in space, far above the shimmer of the atmosphere, doing nothing but measuring the positions of stars with a precision that borders on the absurd. Gaia has charted the locations of nearly 2 billion stars, and it measures their tiny parallax shifts down to angles of a few millionths of a single arc second. To give that some human scale, a millionth of an arc second is roughly the width of a human hair seen from across an ocean. Gaia can watch that hair wobble. With that kind of precision, the parallax bubble has swelled from a few hundred light years to many thousands, taking in a huge swathe of our own galaxy, and pinning down the true distances to exactly the kind of stars the next rung of the ladder depends on. And that is the real gift of parallax. It is not just that it measures the nearby stars, it is that it measures them so well that it can be used to calibrate the rung above it. Because here is the problem that the whole rest of the ladder has to solve. Parallax, even in Gaia's hands, cannot reach another galaxy. The nearest large galaxy to us is more than 2 million light-years away, and at that distance the parallax triangle is thinner than anything we can measure, thinner than anything we are likely to measure for a very long time. If we want to step off of our own galaxy and out into the universe of other galaxies, where the expansion of space actually reveals itself, geometry alone can no longer carry us. We need a new kind of rung. We need a beacon, an object that we can see across millions of light years, an object whose true brightness we somehow already know. Think carefully about why knowing the true brightness would solve everything. If you see a candle flame far off in the dark, you cannot tell from the flame alone how far away it sits. A dim flame could be a small candle nearby or a bonfire far away. But if someone told you with certainty that every one of those flames was in truth a standard candle of exactly known brightness, then the dimness of the flame would instantly tell you its distance. The fainter it looks compared to how bright you know it truly is, the farther away it must be. That comparison between how bright a thing appears and how bright it actually is a distance measurement in disguise. All you need is a class of objects out there in space whose real brightness you can trust. A cosmic candle that always burns at the same known strength. For most of human history, no such object was known. The stars were just points of light, some brighter, some dimmer, with no way to tell whether a bright one was truly luminous or simply close. The sky was a wall of lanterns at unknown distances, and there was no way past the wall. The second rung of the ladder did not exist, and without it the universe beyond our galaxy was, in the most literal sense, immeasurable. It is worth knowing that this first rung was, for most of human history, completely out of reach, and that finally conquering it was a triumph in its own right. The ancient Greeks understood the principle of parallax perfectly well. They reasoned that if the Earth truly moved around the Sun, the nearby stars ought to shift against the distant ones over the course of a year. They looked for that shift, and they could not find it. To some, this was taken as proof that the Earth stood still at the centre of everything. In truth, it was proof only that the stars are far more distant than anyone had dared to imagine, so distant that their parallax shift is far too small to catch with the naked eye. The triangle was there all along, it was simply too thin to see. It took until the year 1838, more than 2 centuries after the telescope was invented, for anyone to finally measure the parallax of a star. A German astronomer named Friedrich Bessel, working with obsessive care, caught the tiny annual wobble of a modest star called 61 Cygni, and from that wobble calculated that the star lay some 10 light-years away. It was the first time a human being had ever measured the true distance to a star beyond the sun, and the distance was so enormous, so far beyond anything in ordinary experience, that it quietly reshaped the sense of scale of everyone who understood it. The nearest stars, it turned out, were not lanterns hung just above the sky. They were suns, unthinkably far away, with almost perfectly empty space stretched between them. Sit with the sizes involved, because they are the reason this rung is at once so trustworthy and so limited. The baseline of the parallax triangle is the width of Earth's orbit, about 300 million kilometers, a distance so large that light itself takes around 16 minutes to cross it. And yet, stretched out to even the nearest stars, that enormous baseline produces an angular shift smaller than the width of a coin seen from many kilometers away. The triangle is real, but it is a needle of a triangle, absurdly long and impossibly thin. This is why parallax is both the most reliable rung and the shortest. It assumes nothing but geometry, so it cannot lie to you. But the angles shrink so quickly with distance that even our finest instruments lose the thread within a few thousand light years. Now return to that image of standing on the Earth and watching a nearby star shift, and feel the machinery underneath it. You're not merely turning your head, you are riding a planet, and the planet is carrying you in a great circle, 300 million kilometers wide, taking a full year to complete the loop. In the summer, you sit on one side of that circle, and you note exactly where a nearby star sits against the faint ones far behind it. Then you wait. Season turns into season. The Earth carries you all the way around to the opposite side of its orbit, and in the winter you look again at the very same star. And it has moved. Not much, a hair's width, but it has moved, drifting against the distant backdrop exactly as your finger drifted when you blinked between your two eyes. That tiny seasonal shift, measured with enough patience, is a direct line to the star's distance, drawn in nothing but angles. It is the one rung of the entire ladder that a geometer from any century in history would recognize and trust on sight. And then, in the first years of the 20th century, in a cramped room at Harvard, someone found the cosmic candle. She was not allowed to operate the telescopes. She was paid by the hour to examine photographs of the sky, one dim smudge at a time. And in those photographs, in the flickering of a particular kind of star, she noticed a pattern so simple and so powerful that it would let the human race finally step off the Earth and begin to measure the true size of the heavens. To climb to the next rung, we have to meet her. Her name was Henrietta Swan Leavitt, and she was one of the reasons we can measure the universe at all. In the early 1900s, the Harvard College Observatory employed a group of women to do the painstaking work of examining photographic plates of the night sky. They were called computers because computing was a job that people did, not a machine, and it meant sitting for long hours cataloguing the position and brightness of star after star after star, by eye, by hand. They were paid a few cents an hour. They were not permitted to run the great telescopes themselves. Leavitt was among the most gifted of them, and she was also, for much of her life, profoundly deaf. She worked in near silence, bent over glass plates, studying a particular kind of star that did something no ordinary star does. It pulsed. The stars she studied are called Cepheid variables, and they are not calm, steady points of light. A Cepheid swells and shrinks, brightens and dims, over a cycle that repeats like a slow heartbeat. Some Cepheids complete that cycle in a couple of days, others take weeks or months, and as they beat, their brightness rises and falls in a smooth, predictable rhythm you could set a metronome to. Leavitt catalogued hundreds and then more than 1,000 of these pulsing stars, many of them clustered together in a faint smudge of sky we call the Small Magellanic Cloud. And because those particular stars were all bunched together in roughly the same place, they were all at roughly the same distance from Earth. That detail turned out to be the key that unlocked everything. Here is what she saw in her patient rows of numbers. Among those stars, all sitting at nearly the same distance, the ones that pulsed more slowly were also, reliably, the brighter ones. A Cepheid with a long, lazy rhythm, taking weeks to complete a beat, shone more powerfully than a Cepheid that flickered through its cycle in a day or two. And crucially, because they were all the same distance away, their apparent brightness in her photographs was a fair reflection of their true brightness. The relationship was clean and simple. The longer the period of the pulse, the greater the true luminosity of the star. Time the heartbeat, and the star tells you how much light it is really pouring out. Sit for a moment with what that means, because it is easy to say quickly and just as easy to miss. Leavitt had found a way to look at a star and know, from nothing but the rhythm of its pulsing, how bright it truly was. Not how bright it appeared, how bright it actually was, in absolute terms, and we said, just a few minutes ago, that a class of objects whose true brightness you already know is exactly the cosmic candle the ladder needs. That is what a Cepheid is. Its pulse period is a label stamped on the side of the candle, telling you its true wattage. Measure how bright it looks from Earth. Compare that to how bright you know it must be, and the difference gives you the distance. Leavitt had turned a beating star into a measuring rod that could reach across the gulfs between galaxies. She published this relationship, this law connecting a Cepheid's period to its brightness, in the years around 1908 and 1912, and then, in one of the quieter injustices in the history of science, the world took her gift and largely moved on without her. Other astronomers used her law to remake the entire map of the cosmos. She continued to be paid by the hour. She was never given a telescope of her own to point at the sky she had unlocked. In 1921 she died of cancer, and a few years later a mathematician who wanted to nominate her for the Nobel Prize discovered, to his dismay, that she was already gone and the prize is not awarded to the dead. The most important measuring tool in astronomy carries her fingerprints on every use, and most people who benefit from it have never heard her name. I want to let that land gently, because it is the human weight underneath all this cold machinery of measurement. Every time an astronomer today reaches across space to time the pulse of a distant star, they are using a rung of the ladder that a deaf woman, working in silence and paid in pennies, built with her own eyes a century ago. When we say later tonight that the local measurement of the universe rests on the distance ladder, this is the foundation we're talking about. Not an abstraction, a person. When the two numbers refuse to shake hands, one of those numbers reaches all the way back down through the rungs to Henrietta Leavitt at her desk, and her law has held up under every test we have ever thrown at it. That is worth remembering when we start hunting for who might be wrong. With Leavitt's law in hand, the ladder suddenly grew tall. Astronomers could now find a Cepheid pulsing away inside another galaxy, time its rhythm, read off its true brightness, see how faint it appeared, and calculate how impossibly far away that galaxy must be. And they anchored the whole thing to the rung below. Remember, parallax gives us rock-solid geometric distances to the nearby Cepheids in our own galaxy. Those nearby Cepheids calibrate the exact relationship between period and brightness. Then that calibrated relationship is carried outward to Cepheids in other galaxies, far beyond the reach of any triangle. This is the ladder working exactly as it should. Geometry on the bottom rung, holding up the beating stars on the rung above, which in turn reach out into the universe of galaxies. Each step trusts the step beneath it. Each step extends the one before, and the distances this revealed were almost impossible to accept at the time. In the early 20th century there was a genuine heated argument about whether our own galaxy, the Milky Way, was the entire universe, or whether the faint spiral smudges scattered across the sky were separate galaxies of their own, island universes floating at unthinkable distances. Leavitt's candle settled it. When astronomers found Cepheids pulsing inside those spiral smudges and measured their distances, the numbers came back so large that there was no longer any doubt. Those smudges were not clouds inside our galaxy. They were other galaxies, hundreds of thousands and then millions of light years away, each one a city of billions of stars. In a single stroke, the known universe swelled from one galaxy to countless galaxies, and the Cepheids were the reason we could say so with confidence. But the ladder was not finished, and neither was the surprise waiting inside those distant galaxies. Because once astronomers could measure how far away the galaxies were, they could pair that distance with another measurement, one that had been quietly gathering for years, having to do with the colour of the light those galaxies sent us. And when someone finally laid the distances of the galaxies beside the colours of their light and plotted one against the other, a pattern jumped off the page that would tear the roof off of our understanding of reality. It would reveal that the universe was not a fixed, eternal stage. It was moving, it was growing, and nobody had seen it coming. It helps to picture the room where this discovery was actually made, because it was nothing like the popular image of astronomy. There was no dome, no eyepiece, no lone genius gazing up at the heavens. There was a table, and good light, and stacks of glass photographic plates, each one a frozen image of a patch of sky captured by a telescope somewhere else, sometimes on another continent entirely. The women who worked here, the computers, spent their days bent over these plates with magnifiers, measuring the size and darkness of thousands upon thousands of tiny black dots, each dot a star. It was considered clerical work, tedious and mechanical, the sort of task handed off to women who were paid a fraction of a man's wage. And yet it was inside this quiet, undervalued labour that one of the keys to the whole universe was quietly turned. What made Leavitt's particular stars special is worth understanding, because the physics of it is genuinely lovely. A Cepheid does not pulse for mysterious reasons. It pulses because it is caught inside a kind of engine, a cycle driven by a layer of gas deep within it. When the star is compressed, that inner layer becomes more opaque, trapping heat, which builds pressure, which pushes the star to swell outward. As it swells, the layer turns more transparent again, the trapped heat escapes, the pressure drops, and gravity pulls the star back inward to begin the cycle once more. The star breathes, in and out, on a rhythm set by its own size and mass. A larger, more luminous Cepheid is like a larger bell, ringing more slowly, taking longer to complete each breath. A smaller one rings faster, and that is the deep reason the period is tied to the brightness. The rhythm of the pulse is a direct readout of the size of the star, and the size of the star sets how much light it pours into space. Leavitt catalogued more than 1,700 of these variable stars over the course of her work, and it was among a particular set of them, all clustered together in the small Magellanic Cloud, that she drew out the clean, simple law connecting the length of the pulse to the true brightness of the star. She could not have known in that moment that she had just handed astronomy the one tool it had been missing for all of human history. The law itself was modest, a relationship you could plot on a single sheet of paper. But that modest relationship is the reason we can measure the distance to galaxies millions of light-years away, and it is the reason, in the end, that we have one of our two disagreeing numbers at all. I keep returning to the injustice of her story, and I do it on purpose, because it matters for how we hold this whole mystery tonight. It is tempting to imagine that our knowledge of the universe was built by a handful of famous men on mountaintops, but the truth is quieter and far more human than that. The foundation of the cosmic distance ladder was laid by a deaf woman, working for pennies, who was never permitted to point a telescope at the sky she unlocked, and who died before the world thought to honour her. When a mathematician tried, years later, to nominate her for the highest prize in science, he learned she had already been gone for several years, and the prize is never given to the dead. Her law outlived her, and it still holds today. Every time an astronomer times the pulse of a distant Cepheid to measure how far away a galaxy sits, they are trusting Henrietta Leavitt, whether they speak her name or not. To witness that moment, we have to leave Harvard behind and climb a mountain in California on a cold night near the end of the 1920s, where two very different men were about to catch the entire universe in motion. Picture the top of Mount Wilson, in the hills above Los Angeles, on a clear cold night near the end of the 1920s. The air is thin and still. Inside a great domed building sits the 100-inch Hooker telescope, at that time the largest and most powerful eye ever turned on the sky. The dome is unheated, because heat makes the air shimmer and blurs the stars, so the men working through the night wear heavy coats and breathe out fog. One of them is a former mule driver named Milton Humason, who had come to the observatory hauling equipment up the mountain trail and worked his way up from janitor to become one of the most skilled observers alive. He sits at the telescope for hours in the dark, guiding it with tiny corrections, keeping a single faint galaxy locked in place, while its light trickles down onto a photographic plate, drop by drop, sometimes across entire nights, gathering enough of that light to spread it into a spectrum. The other man, more famous, more polished, is Edwin Hubble, who takes those distances and those spectra and looks for a pattern. The spectrum was the crucial thing. When you spread a galaxy's light out into its colours, like sunlight through a prism, you find dark lines cutting across it, fingerprints left by the elements in the stars. Astronomers knew exactly where those fingerprint lines should sit, but in the light of distant galaxies the lines were not where they belonged. They were shifted, all of them together, toward the red end of the spectrum. This is the famous redshift, and its cause is beautifully simple. When a source of light is moving away from you, the waves of that light get stretched, and stretching light shifts its colour toward red. The faster the galaxy flees, the more its light is stretched and the more its fingerprint lines slide toward the red. Humeson's painstaking spectra were, in effect, speed measurements. Each one told Hubble how fast a given galaxy was rushing away from us. Now Hubble had two numbers for each galaxy. He had the distance, measured by the Cepheids, using Leavitt's law and the ladder we just built, and he had the speed, measured by the redshift in Humeson's spectra. In 1929, he plotted one against the other, distance along one axis, speed along the other, a scatter of dots for the galaxies they had managed to measure. And the dots did not scatter randomly. They lined up. They fell along a rising slope, climbing from the bottom left to the upper right. The farther away a galaxy was, the faster it was receding, and not in a vague way, but in a clean, straight, proportional line. Double the distance and you double the speed of retreat. It was one of the most consequential graphs ever drawn. Let yourself stand in that dome for a moment and feel what that rising line meant. If every galaxy is fleeing, and the distant ones flee faster in exact proportion to their distance, then there is only one sensible picture that fits. Space itself is expanding. Not the galaxies flying apart through some fixed and empty stage, but the stage itself stretching, swelling in every direction, carrying the galaxies along with it. Imagine raisins set into a loaf of bread dough as it rises in the oven. Every raisin drifts away from every other raisin, and from the point of view of any single raisin, the farther ones recede fastest, simply because there is more expanding dough between them. There is no centre. Every raisin sees the same thing. That is the universe Hubble had stumbled into. Until that night, the cosmos had been imagined as eternal and unchanging, a settled and permanent thing. In a single graph, it became something that had a history, something that was growing, something that must once have been smaller, denser, and hotter. The universe, it turned out, was not a place. It was a process. That rising slope had a steepness, and the steepness was the very first measurement of the number we started with tonight, the Hubble constant. It is the rate at which speed climbs with distance, the tilt of that fateful line. And here is a detail that should make you feel tender toward this whole difficult enterprise, rather than smug about it. Hubble's first value for the expansion rate was wildly, enormously wrong. He got a number around 500, roughly 7 times larger than the value we accept today. His ladder had a flaw in it. The calibration of the Cepheids was off, and there were different kinds of pulsing stars tangled together that nobody had yet learned to separate. The rung had a crack, and because the expansion rate also gives the age of the universe, Hubble's wrong number implied a universe younger than the known age of the rocks on Earth, which was plainly impossible. The cosmos could not be younger than the planet inside it. I point this out not to mock the past, but because it is the heart of tonight's story in miniature. The very first measurement of the expansion rate was wrong, and it was wrong because a rung of the ladder was miscalibrated. Over the following decades, astronomers found the flaw, untangled the different kinds of variable stars, rebuilt the rung, and the number came down and down, from 500 toward 100, and then further, settling over many years into the neighbourhood it occupies now. That is measurement working the way it is supposed to. You find the error, you fix the rung, the number converges. Everyone assumed that this convergence would simply continue, tightening forever toward one final, agreed value. For most of the 20th century, that is exactly what seemed to be happening. The disagreements were large at first, a factor of 2 between rival camps. Then they narrowed, and the field crept toward consensus. Keep that history in your mind, because it is precisely why the modern tension is so unsettling. We have been here before, with a mismeasured expansion rate, and every previous time the problem turned out to be a flaw in the ladder that better work eventually repaired. So when the two numbers began to disagree again in our own century, the natural assumption, the assumption backed by 100 years of experience, was that history would repeat. Someone had a crack in a rung. Find it, fix it, and the numbers would slide together the way they always had. That is what nearly everyone expected. That is what the astronomers themselves expected. The redshift at the heart of this discovery deserves a closer look, because it is subtler and stranger than it first appears. When you hear that a galaxy's light is shifted toward red because the galaxy is moving away, it is easy to picture the galaxy flying off through space like a car speeding down a road. Its light stretched the way a siren drops in pitch as it passes you. That picture is close, but not quite right, and the difference matters more than you would think. The galaxies are not, for the most part, racing away through space. They are being carried apart by the expansion of space itself. The light is not stretched because the galaxy is speeding through the emptiness. It is stretched because the very space the light is crossing has grown while the light was in transit. A wave of light set out from a distant galaxy billions of years ago, and during its long journey, the cosmos expanded and the wave was stretched along with everything else, arriving here longer and redder than when it began. The redshift is not really a speed at all. It is a record of how much the universe has grown since the light departed. It is also only fair to say that Hubble did not do this alone, and that history has been a little unkind in the other direction here. Years before Hubble drew his famous graph, an astronomer named Vesto Slipher had already measured the redshifts of many spiral galaxies, patiently gathering the spectra that showed most of them fleeing from us. And a Belgian priest and physicist named Georges Lemaitre had, 2 years before Hubble's paper, worked out the mathematics of an expanding universe and even estimated the rate of expansion from the data available at the time. The idea was in the air, assembled from many hands. Hubble's contribution was to bring the distances and the redshifts together cleanly enough that the rising line became impossible to deny. Science is almost never one person shouting a discovery from a peak. It is a slow accumulation, a relay of careful people passing the work forward, each one adding a rung. And then there is Milton Humason, who deserves to be remembered every bit as much as the famous names. He had almost no formal schooling. He came to Mount Wilson as a young man leading mule trains up the mountain, hauling the very equipment used to build the observatory, and he took a job there as a janitor. But he had steady hands, endless patience, and a quiet gift for the delicate art of guiding a telescope through the long, cold hours of the night. He worked his way up from sweeping floors to operating the greatest telescope in the world, sitting nearly motionless in the dark, coaxing the faint light of distant galaxies onto photographic plates across entire nights. The speed measurements that made Hubble's discovery possible came from Humason's exposures, a former mule driver gathering the light that would reveal the expansion of the universe. There is something in that pairing, the polished astronomer and the self-taught observer, that captures how this knowledge actually gets made. Return, for one last moment, to that cold dome in 1929 and hold the image, because it is one of the true turning points in the history of human thought. 2 men, working through the night in heavy coats and fog, one plotting distances he owes to a deaf woman at Harvard, the other guiding the great mirror with the hands of someone who once led mules up the mountain trail. On the plate, the fingerprint lines of distant galaxies all shifted toward red. On the paper, the dots climbing along their rising line, and in that rising line, without any fanfare at all, the quiet end of the old, eternal, unchanging cosmos. Until that night, the universe had a past no different from its present, a still and permanent thing. After that night, it had a history. It had a beginning. It was going somewhere. Everything we have argued about since, including the 2 numbers that will not shake hands, begins on the rising slope those 2 men found together in the dark. But before we can understand why that expectation broke, we have to finish building the ladder, because the Cepheids, magnificent as they are, still could not reach far enough. To measure the expansion rate cleanly, you need to see galaxies so distant that the local swirling of nearby galaxies no longer muddies the reading, galaxies whose retreat is purely the stretching of space. Cephids, at those distances, become too faint to pick out. The ladder needed one more rung, one final beacon brighter than any pulsing star, bright enough to be seen most of the way across the observable universe, and nature, as it happens, provides one. It provides it in the form of a dying star that detonates with the light of billions of suns. There is a particular kind of stellar death that behaves with uncanny consistency, and it became the top rung of the ladder. It begins with a white dwarf, the dense, cooling ember left behind when a star like our sun runs out of fuel. A white dwarf is a strange object, about the mass of the sun packed into a ball the size of the Earth, so dense that a spoonful of it would weigh as much as a truck. On its own, a white dwarf simply sits and cools for ages. But if it has a companion star nearby, it can siphon material off of that companion, gaining mass, growing heavier and heavier until it crosses a very precise threshold. There is a specific limit, a particular mass, beyond which a white dwarf can no longer hold itself up against its own gravity, and when it reaches that limit it detonates. The entire star tears itself apart in a runaway thermonuclear explosion, flaring for a few weeks with the brilliance of billions of stars, bright enough to briefly outshine the whole galaxy that hosts it. We call this a Type Ia supernova. The reason this matters for measuring the universe is hidden in that precise threshold. Because these white dwarfs all detonate at very nearly the same mass, tipping over the same gravitational cliff, they all release very nearly the same amount of energy. They all flare to nearly the same true brightness. In other words, a Type Ia supernova is a standard candle, exactly like a Cepheid, but almost unimaginably brighter. A Cepheid can be seen across tens of millions of light years. A Type Ia supernova, blazing with the light of billions of suns, can be seen across billions of light years, most of the way to the edge of the observable universe. Here at last was a beacon bright enough to measure the deep cosmos and steady enough to trust, and it slots into the ladder with the same patient logic as every rung before it. When a Type Ia supernova erupts in a nearby galaxy, one close enough that we can also see individual Cepheids pulsing inside it, we use the Cepheids to measure that galaxy's distance, and that distance tells us the supernova's true brightness. Now we know exactly how bright these explosions really are, so when one erupts in a galaxy far too distant for any Cepheid to be seen, we simply compare how bright it appears to how bright we know it must be, and we read off the enormous distance. Parallax calibrates the Cepheids. The Cepheids calibrate the supernovae. The supernovae carry us to the far reaches of space. The whole ladder, from the triangle in your backyard to an exploding star halfway across the universe, standing on that single foundation of geometry, each rung anchored to the one beneath it. In the late 1990s, two competing teams of astronomers set out to use these exploding stars for an ambitious purpose. They wanted to measure not just how fast the universe is expanding, but how that expansion was changing over time. Everyone expected the expansion to be slowing down. After all, the universe is full of matter, and matter has gravity, and gravity pulls things together. The sensible expectation was that the collective gravity of everything should be gently putting on the brakes, slowing the expansion, the way a ball thrown upward is slowed by the Earth's pull. The two teams raced to measure the size of that cosmic braking. They gathered distant supernovae, compared their brightness to their redshifts, and prepared to announce how quickly the universe was decelerating. What they found instead, in 1998, stopped both teams cold and rewrote cosmology. The distant supernovae were fainter than they should have been. They were farther away than a decelerating universe could explain. The expansion was not slowing down at all. It was speeding up. Something was pushing the universe apart faster and faster, overwhelming the inward pull of all the matter it contains. The two rival teams, checking each other, arrived at the same impossible answer, and the discovery was so solid and so shocking that it earned a Nobel Prize. We had assumed the cosmos was coasting to a stop. Instead, it was accelerating into the dark. Whatever is causing that acceleration got a name, though the name is really just a label for our ignorance. We call it dark energy. It appears to be a property of empty space itself, a faint pressure woven into the vacuum that pushes outward, and it is not a minor ingredient. When you add it all up, this dark energy accounts for roughly 68% of everything in the universe, more than 2/3 of all there is, and we do not know what it is. Sit with that quietly, because it is one of those facts that should reorganize how you see the sky. The dominant component of reality, the thing that makes up most of the cosmos, is a form of energy we cannot identify, detected only by the way it stretches space. Everything you have ever seen or touched, every star, every galaxy, all the ordinary matter in existence, is a minority ingredient in a universe ruled by something invisible. I raise dark energy here for two reasons. The first is that it is woven directly into the number we are chasing, because the way the universe expands over time depends on how much dark energy there is, and whether its strength stays constant. The second reason is quieter, and it is a theme worth naming out loud. We have now reached the top of the local ladder, the exploding star rung, and it hands us a value for the expansion rate of around 73. That is one of our two numbers, and notice that even at its proudest moment, when the ladder is complete and reaching across billions of light years, it is already entangled with a substance we do not understand. The ladder is magnificent. It is also standing in a universe most of which is a mystery. That is the humbling backdrop to everything that follows. So we have our first number, 73, built from the ground up, rung by rung, geometry to pulsing stars to exploding stars, a century of careful work, anchored in the honest triangles of parallax and carried outward by the light of dying suns. If this were the only way to measure the universe, we would simply accept it, refine it, and move on. The value would tighten over time, and the age and size of the cosmos would settle into place, and there would be no crisis, no tension, no two numbers refusing to meet. There is a detail hidden in that precise threshold that is worth naming, because it turns the whole thing from a curiosity into a tool you can genuinely trust. The mass limit a white dwarf cannot exceed is not arbitrary. It is a specific number, worked out in the 1930s by a young physicist named Subrahmanyan Chandrasekhar, who calculated that a white dwarf heavier than about 1 4/10 times the mass of the Sun simply cannot hold itself up. Below that limit the star endures. Above it, gravity wins, and the star collapses and detonates. Because every one of these explosions is triggered at the same critical mass, they all release close to the same amount of energy. That is the physical reason a Type Ia supernova is a standard candle. It is not a coincidence, or a lucky pattern. It is written into the physics of how these particular stars die. In practice, these explosions are not perfectly identical, and the way astronomers handle that imperfection is its own small triumph, worth appreciating. Some Type Ia supernovae are a little brighter than others, but it turns out that the brighter ones fade more slowly, and the dimmer ones fade more quickly, in a reliable and measurable way. By watching how fast a supernova brightens and then dims over the following weeks, astronomers can correct each one back to a common standard, sharpening a rough candle into a precise one. This means they are not simply hoping the explosions are all the same. They are measuring the shape of each explosion's light and adjusting for the differences, one supernova at a time. The candle is not calibrated once and trusted forever. It is calibrated every single time it is used. When the two teams set out in the 1990s to measure the expansion history with these candles, they were attempting something genuinely daring. They were gathering supernovae so distant that their light had been travelling for billions of years, comparing the faint glow of an exploding star against how bright they knew it truly had to be, and reading off both its distance and, through its redshift, how much the universe had grown since that light left. Two independent groups working in competition, each braced to announce how quickly the cosmos was slowing down. And when both groups, checking against one another, found instead that the distant explosions were too faint, too far away, that the expansion was speeding up rather than breaking, the result was so unexpected that they spent months hunting for the mistake before they would believe it themselves. There was no mistake. The universe really is accelerating. The thing doing the accelerating, this dark energy, is worth lingering on precisely because it is so poorly understood and because it sits right in the middle of the number we are chasing. It behaves like a pressure built into empty space, a tendency of the vacuum itself to push outward. The more space there is, the more of this outward push there is. So as the universe grows, the acceleration grows along with it. And when we account for how much of it there has to be to explain what we see, it comes out to roughly 68% of the entire contents of the universe. More than 2/3 of everything is this substance we cannot name, revealed only by the way it stretches the cosmos apart. That is the strange soil in which the very top rung of our ladder is planted. We have measured the expansion rate to within about 1%, and yet the dominant ingredient driving that expansion remains to this day little more than a placeholder word for something we do not understand. It is worth holding, for just a moment, the sheer reach of this final rung, because it is easy to say billions of light years and feel nothing at all. When one of these white dwarfs detonates, it briefly shines with the light of billions of ordinary stars, bright enough that a single dying star can rival the glow of the entire galaxy it sits inside. That is why we can see them across almost the whole observable universe. It means the top rung of our ladder is not a faint, delicate thing straining at the very limit of detection. It is a beacon of almost absurd power, calibrated by the pulsing seafeeds below it, which are in turn calibrated by the geometry below them. Stand back and take in the full height of the structure. A triangle in the backyard holding up a beating star, holding up an exploding star visible halfway to the edge of everything. Each rung modest on its own, and together they reach farther than any single measurement has any right to. This is the tower that gives us 73, and it is a genuine wonder of human patience, whatever its quarrel with the ancient light turns out to mean. But there is another way to weigh the expansion of the universe. It does not use the ladder at all. It does not use nearby stars or exploding white dwarfs or any of the beacons we have spent this time building. It reaches instead all the way back to the beginning, to a moment less than 400,000 years after the birth of everything, and reads the expansion rate directly from a photograph of the infant cosmos. It is completely independent. It shares not a single rung with the ladder we just climbed, and it comes back with a different answer. Close your eyes for a moment and travel back with me, not thousands of years, not millions, but all the way back to when the universe was only about 380,000 years old. Before there were stars, before there were galaxies, before there was a single point of light anywhere in the sky, because the whole cosmos was one uninterrupted glow. Everything that now exists is packed into a space far smaller and far hotter than it is today. A searing fog of bare particles, protons and electrons and light, all crushed together at thousands of degrees. It is too hot for atoms to hold together. Every time an electron tries to settle onto a proton to form an atom, a passing particle of light knocks it loose again. Matter and light are locked in a single seething plasma, and that plasma fills absolutely everything. Now feel what is happening inside that fog, because it is the key to the second number. The plasma is not perfectly smooth. There are slightly denser regions and slightly thinner ones, and gravity pulls matter toward the dense spots, while the intense pressure of the trapped light pushes back out. Pull in, push out, pull in, push out. The whole universe is ringing, like the inside of an enormous bell with pressure waves rolling through the plasma. These are quite literally sound waves, sweeping through the fire of the young cosmos at a good fraction of the speed of light. The entire universe is humming a single immense chord, and those waves are travelling outward from every dense clump, in every direction, spreading at a known speed for a known amount of time. Then, in what feels like an instant on the cosmic clock, the universe expands and cools just enough to cross a threshold. It becomes cool enough for the electrons to finally settle onto the protons and stay there, forming the first neutral atoms, and the moment that happens, the fog clears. The light that had been endlessly bouncing between particles is suddenly set free, released to travel in straight lines across a newly transparent universe. That liberated light has been streaming outward ever since, for more than 13 billion years, stretched by the expansion of space into faint microwaves, until it washes over us now as a whisper of radiation coming from every direction in the sky. We call it the cosmic microwave background, and it is, in the most literal sense, a photograph of the universe as an infant, the oldest light there is. When the fog cleared, the sound waves froze. The pattern of denser and thinner regions they had created was locked into place, printed onto that ancient light like a snapshot of the last chord the universe ever hummed as a single body. And here is the beautiful, decisive point. Because those sound waves all travelled at a known speed for a known length of time before the fog cleared, they all reached the same characteristic distance. That distance, the farthest a pressure wave could travel in the infant universe before everything froze, is called the sound horizon, and it is about 150 megaparsecs, roughly 490 million light-years across. It is a ruler of known length, forged in the first moments of the cosmos and stamped onto the sky for us to find. And when we photograph the cosmic microwave background in exquisite detail, we can see the imprint of that ruler directly, in the characteristic size of the warm and cool patches speckled across the ancient light. A spacecraft called Planck spent years doing exactly this, mapping the temperature of that background light across the entire sky with extraordinary precision, measuring patches that differ from one another by less than 1 part in 100,000. From that map, cosmologists can measure how big the sound horizon ruler appears on the sky. And here is where the magic happens. A ruler of known true size appearing at a certain apparent size tells you how far away it is, and how much the universe has expanded in the time since the light left it. Feed that measurement into the standard model of cosmology, the carefully tested framework describing how a universe full of matter and dark energy evolves, and the equations hand you the expansion rate. No parallax, no Cepheids, no exploding stars, no ladder at all. Just the frozen ringing of the newborn universe, read directly off the oldest light in existence. This second road is a triumph every bit as great as the ladder, and in some ways it feels even more secure, because it depends on simple, well-understood physics in the early universe rather than a long chain of calibrations. It is clean, it is independent, It shares nothing with the local method. Two completely separate ways of weighing the same expanding universe, one built upward from the ground through a century of patient rungs, the other reaching straight back to the dawn of time and reading the answer off a baby photograph. Every instinct says they must agree. They are measuring the same universe. There is only one universe, and it has only one true rate of expansion. If both methods are sound, the two numbers should land on top of each other. But when Planck read the expansion rate off the cosmic microwave background, using the frozen sound horizon as its ruler, the number that came back was not 73. It was about 67.5, lower, slower, and measured with an uncertainty so small that there was very little room to wave the difference away. The early universe, read directly, insists the cosmos is expanding more slowly than the ladder of nearby stars insists it is. Two roads, two numbers, and a gap between them that has no business existing. For a while, when both measurements still had a bit of wobble in them, you could squint and hope. Maybe the error bars were a little larger than admitted. Maybe the two numbers were secretly reaching toward each other and would meet once the measurements improved, exactly as history promised they always did. That was the comfortable expectation, and almost everyone shared it. The tension was small, the uncertainties were real, and the long experience of astronomy said that better data would heal the rift. All anyone had to do was wait, and measure more carefully and watch the gap close. It is worth pausing to appreciate that this ancient light was not neatly predicted and then dutifully found. It arrived almost by accident, and the story of its discovery has become one of the small legends of science. In the mid-1960s, two researchers at a laboratory in New Jersey were working with a large sensitive antenna, and they kept picking up a faint, steady hiss of microwave radiation they could not get rid of. It came from every direction in the sky, day and night, in every season. They checked their equipment obsessively. They even cleaned out the droppings of pigeons that had nested inside the antenna, suspecting the birds might be the source. Nothing they did made the hiss go away, because the hiss was not a flaw in their instrument at all. It was the afterglow of the birth of the universe, the very light we've been describing, washing over the Earth from all sides at once. They had stumbled onto the oldest light in existence while trying to eliminate what they assumed was noise. That faint hiss turned out to be one of the most important discoveries in the history of cosmology, because it confirmed that the universe really did begin in a hot, dense state, and has been expanding and cooling ever since. And as the instruments improved, astronomers realized that this background light was not perfectly smooth. It carried a faint pattern, a speckle of very slightly warmer and cooler patches, differing from one another by less than 1 part in 100,000. Those minuscule variations are the frozen imprint of the sound waves we described, the ringing of the infant cosmos, captured at the instant the fog cleared, and crucially, the characteristic size of those patches is set by how far the sound waves managed to travel before they froze, which is the sound horizon, our ruler of known length. The Planck spacecraft, which mapped this background light for years from a stable point far beyond the Moon's orbit, measured those patches with such precision that it could pin down the size of the sound horizon ruler, and, through it, the whole geometry and history of the early universe. From that single map, cosmologists extract not only the expansion rate but the age of the universe, the amount of ordinary matter, the amount of dark matter, and the amount of dark energy, all at once, all consistent with one another. It is one of the most tightly constrained measurements in all of science, and it is precisely because that measurement is so tight, so internally consistent and so thoroughly checked, that its answer for the expansion rate 67.5 cannot be casually brushed aside. This is not a rough guess. It is one of the most careful measurements humanity has ever made, and there is an independent way to see the very same ruler, which makes the early number harder still to wave away. That frozen ring of primordial sound did not only leave its mark on the ancient light, it also left a faint preferred distance in the way galaxies are scattered across the sky today. If you map millions of galaxies and measure the separations between them, you find a subtle extra tendency for pairs of galaxies to sit about that same characteristic distance apart, the sound horizon, grown along with the expanding universe. Astronomers have measured this pattern in enormous galaxy surveys, and it confirms the ruler independently, from the modern universe rather than the ancient light. So the early universe road is not one fragile measurement standing alone. It is a web of cross-checks, and they all point to the same low number. Take a step back and feel the shape of what we now hold. On one side, the ladder, built upward from geometry through pulsing stars to exploding stars, confirmed rung by rung, giving about 73. On the other side, the ancient light and the frozen sound ruler, cross-checked against the scattering of galaxies, giving about 67.5. Two roads that could hardly be more different in their methods, their instruments, their eras, and their assumptions, and yet both are measuring the one true expansion rate of the one universe we live in. There is only one honest expectation left. They should agree. There is one more thing worth saying about why the early number carries so much authority, and it has to do with how much else it gets right at the same time. The same reading of the ancient light that gives the low expansion rate also predicts, with quiet accuracy, the proportions of the lightest elements forged in the first few minutes of the universe, the amount of ordinary matter, the amount of dark matter, and the precise speckled pattern of warm and cool patches across the entire sky. It is not a lonely figure pulled from a single measurement. It is one thread in a picture so tightly woven that tugging on it disturbs everything else. That is a large part of what makes the disagreement so serious. If the early number is wrong, it is not wrong in isolation. It is wrong in a way that should have shown up somewhere else in that beautifully consistent picture, and it has not. The ancient light is not guessing. It is one of the most complete and self-consistent measurements we have ever made, and it insists calmly and stubbornly on 67.5. So they waited, and they measured more carefully, and the gap did not close. This is the moment the story turns, the moment the comfortable expectation begins to fail, and to understand it we need to stop building and step back. We need to lay the two roads side by side in full daylight and look honestly at the two numbers that will not shake hands. Let us stop building for a moment and put the whole picture together, plainly, in one place, because we have gathered a great deal and it helps to set it side by side. We began with a single number, the expansion rate of the universe, the rate that fixes its age and its size. We found that there are two great ways to measure it, and we have now walked all the way up both of them. The first road is the ladder. It starts on the solid ground of geometry, with the parallax of nearby stars, pure triangles that assume almost nothing. Those triangles calibrate the pulsing Cepheid stars, using the law a deaf woman at Harvard found in the flicker of her photographic plates. The Cepheids in turn calibrate the exploding white dwarfs, the Type Ia supernovae, standard candles bright enough to be seen across billions of light years. Rung upon rung, each anchored to the last, reaching from your backyard out into the deep cosmos. And when you climb all the way to the top and read off the expansion rate, the ladder says the universe is expanding at about 73. The second road never touches the ladder at all. It reaches back to the infant universe, to the light released when the primordial fog first cleared, the cosmic microwave background. It finds, printed on that ancient light, the frozen ring of the sound waves that once swept through the newborn plasma, a ruler of known size forged in the first hundreds of thousands of years. It measures how large that ruler appears on the sky, feeds it through the well-tested physics of the early universe, and reads off the expansion rate directly. And the early universe says the cosmos is expanding at about 67.5, 73 from the nearby universe of stars, 67.5 from the dawn of time. These are the two numbers that will not shake hands. The gap between them is about 9%, and I want to be honest about how small that sounds and how large it actually is. If two friends estimated the length of a room and came back 9% apart, you would shrug. But these are not casual estimates. These are two of the most obsessively refined measurements in the history of science, each one carrying an uncertainty of only 1% or so. It is not that one measurement is fuzzy and happens to overlap the other. Each number is sharp, each is confident, and they land in different places with clear space between them. The universe is being asked one simple question: how fast are you growing? And it appears to be giving two different answers depending on who is asking. For years, the sensible reaction to this was patience, and it is worth understanding why, because the patience was not foolish. It was earned. Remember Hubble's first value of 500, wrong because a rung of the ladder was miscalibrated. Remember how the number came down over decades as astronomers found their errors and rebuilt their rungs. The entire history of this measurement is a history of disagreements that eventually healed every single time once someone located the flaw. So when a new gap opened between the ladder and the early universe, the accumulated wisdom of a century said, quietly and reasonably, that this too would heal. Somebody had a subtle error. Perhaps the sea feeds were being misjudged. Perhaps there was dust dimming the supernovae. Perhaps something in the reading of the ancient light was off. Find it, fix it, and the numbers would slide together the way they always had before. There is a genuine comfort in that expectation, and it is a comfort worth naming, because losing it is a large part of what makes this story land the way it does. As long as the disagreement is a mistake, the universe is fine. Our picture of the cosmos is intact, and the only thing that needs correcting is us. A mistake is reassuring. A mistake means the tools slipped, not that reality is stranger than we thought. Everyone involved would have been perfectly happy to find a mistake. Careers are not damaged by finding a subtle calibration error and correcting it. The whole field was, in a sense, rooting for a mistake, because a mistake is the outcome that lets everything stay the way it was. And so, over the past decade and more, astronomers went looking for the mistake, harder than they have ever looked for anything. They did not defend their numbers and walk away. They attacked them. Every rung of the ladder was pulled out, examined, stress-tested, and rebuilt. Every assumption in the reading of the ancient light was questioned and re-questioned. The people who measured 73 tried their hardest to make it fall to 67, and the people who measured 67 checked whether it could climb to 73. This is science working exactly the way it should, with each side trying to break its own result before anyone else can. What happened over that decade of hunting is the strangest part of the entire story, and it runs against everything a century of experience had promised. The measurements did not get fuzzier and overlap. They got sharper. The error bars shrank on both sides, and as they shrank, the two numbers did not drift together. They stayed exactly where they were, 73 and 67.5, growing more certain, more sharply defined, more impossible to reconcile with every passing year. The gap did not heal, it hardened into place, and the hunt for a mistake, the search everyone assumed would quietly rescue the old picture, began instead to close every door one after another until there was almost nowhere left for a mistake to hide. Let me put the disagreement in more familiar terms, because numbers can stay abstract until you translate them into something you can hold in your hand. Imagine you owned two exquisite clocks, each built by a master, each certified accurate to within a single second across an entire year. You set them both by the same reference and let them run. And after a year, they disagreed, not by a second, but by more than a month. You would not shrug that off. You would know, with certainty, that something you did not understand was at work, because two clocks that good are not supposed to drift a month apart. That is precisely the situation cosmology is in. These are not sloppy guesses that happen to miss each other. They are two master instruments, each certified to within a percent, disagreeing by 9. The precision is exactly what makes the disagreement intolerable. If the measurements were rougher, there would be no tension at all. It is their sharpness that turns a small gap into a crisis. Or think of it as two maps of the same country, drawn by two teams who never once spoke to each other. One team surveyed on foot, starting from a single fixed landmark and measuring outward, town by town, road by road, all the way across the land. The other team photographed the whole country at once from high above and measured everything from the picture. Both maps are careful, both are internally consistent, and when you lay one on top of the other, they do not match. The scale is off by 9%. Every distance on one map is stretched compared to the other, so which map is wrong? The unsettling answer emerging from all this work is, perhaps neither. Perhaps both maps are accurate, and the mismatch is telling you something true and strange about the country itself, something neither team ever thought to put into their assumptions. I want to dwell on the psychology of the people involved, because it is a part of the story that rarely gets told, and it changes how the whole thing feels. It would be easy to picture two rival camps, each stubbornly defending its own number out of pride. That is not what has happened. The remarkable thing is that both sides have spent years trying to demolish their own results. The astronomers who measure 73 have gone looking again and again for the error that would drag their number down to 67, because finding that error would be a triumph, a resolution, a relief. The cosmologists who read 67 from the ancient light have probed their own analysis for anything that might push it up towards 73. Everyone, on some level, has been quietly rooting for a mistake, because a mistake is the outcome that keeps the universe familiar. And the fact that no one, on either side, has managed to find the fatal flaw despite genuinely wanting to find it, is exactly what has turned a curiosity into a crisis. It helps, too, to remember how many times before this kind of disagreement has healed, because it explains why the tension was shrugged off for so long, and why its refusal to heal is so jarring now. We already saw that Hubble's very first measurement of the expansion rate was off by a factor of 7, wrecked by a single miscalibrated rung. Over the following decades, as the floor was found and the ladder rebuilt, the number tumbled from 500 toward 100, and then rival camps settled into a long argument between roughly 50 and roughly 100, a full factor of 2 apart. That argument, which ran for much of the 20th century, eventually resolved. Better instruments, including a certain famous space telescope launched in part to settle exactly this question, brought the warring numbers together into the 70s, and for a brief, hopeful stretch, it looked as though the expansion rate had finally been pinned down for good. The entire history of this measurement is a history of large disagreements that shrank and then vanished once someone located the error. That is the backdrop against which the modern tension has to be understood, and it is why the first reaction of nearly everyone was calm. We have been here before, many times over. A gap opens, people hunt for the flawed rung, they find it, they fix it, the gap closes. It had become almost a ritual. So when the ladder and the ancient light began to disagree in our own century, the expectation was not alarm. It was patience. Give it time, sharpen the tools, the numbers will converge the way they always have. Nobody expected that this time would be different. Nobody expected that the harder everyone looked, the more solid the disagreement would become, until it crossed the very threshold that physics reserves for genuine discoveries and simply stayed there, immovable. To feel the weight of that, we have to follow the hunt itself. We have to watch the astronomers chase down every possible error, one by one, and we have to watch, with a slowly rising unease, as each suspect is questioned and released. Because the more places they looked for the flaw, the more certain it became that there was no flaw to find. The hunt for the mistake was methodical, and it started with the most obvious suspect, the ladder, because a long chain of calibrations offers many places for a subtle error to hide. Think about everything that could go wrong along the way. The parallax of the nearby stars had to be exactly right. The relationship between a Cepheid's pulse and its brightness had to hold not just here, but in other galaxies with different chemistries. The supernovae had to be truly standard, not secretly varying from one galaxy to the next. Dust floating in space had to be accounted for, because dust dims and reddens starlight and could fool the measurements. Any one of these, if mishandled, could shift the top of the ladder away from its true value. So the astronomers went through them one at a time, with the focused intensity of people who genuinely wanted to find something broken. They tested whether the chemistry of a galaxy changed how it Cepheid's pulse, and folded the correction in. They used the ever-improving parallaxes from the Gaia spacecraft to nail down the bottom rung more firmly than ever. They gathered more and more supernovae to beat down the statistical noise. They cross-checked the dust. And through all of it, the number at the top of the ladder barely moved. It sat there, stubbornly, near 73, refusing to fall towards 67 no matter how hard the ladder was shaken. Every correction they applied was real and worth doing, and not one of them closed the gap. The ladder, examined more closely than it had ever been examined, simply kept giving the same answer. Then there was a second, independent way to check the ladder, and it deserves its own moment because it is where the story gets genuinely subtle and honest. A veteran astronomer named Wendy Friedman, someone with a long and distinguished history of measuring the expansion rate, decided to rebuild the local measurement using a different rung entirely. Instead of relying on Cepheids, she used a different class of stars, the very brightest red giants, at a particular stage of their lives where they all reach the same known peak brightness, before changing. This method is called the tip of the red giant branch, and it is a completely separate way of calibrating the distances to the nearby galaxies that host the supernovae. If the Cepheids were secretly leading everyone astray, this independent method should expose them, and the number should fall. The value that Friedman's red giant method returned was around 69 or 70. And here is the honest, uncomfortable truth of it. That number sits in between. It is a little lower than the Cepheid value of 73, and a little higher than the early universe value of 67.5, and it does not land cleanly on either side. To some, this suggested the tension might be softer than it appeared, that perhaps the Cepheid measurement was running a touch high, and the true answer sat somewhere in the murky middle. To others, the red giant number was still clearly closer to 73 than to 67, and still fundamentally at odds with the early universe. This disagreement within the local camp is real, and I will not paper over it, because the honest picture is not a clean two-sided battle. It is a genuine, ongoing argument in which careful people, looking at overlapping data, still reach somewhat different conclusions. What almost none of them found, though, was a clean path all the way down to 67. The early universe number remained the outlier, sitting low and alone, and nothing in the local measurements would come down to meet it. Meanwhile, the significance of the gap kept climbing, and this is the number that turns unease into something colder. Early on, the disagreement stood at around 2 or 3 sigma, the sort of tension that could plausibly be a statistical accident, the kind of thing that sometimes evaporates on its own. But as both sides sharpened their measurements, the significance rose. It passed 4 sigma, then it reached 5 sigma, and then beyond. Recall what 5 sigma means. It is the discovery threshold, the line beyond which physicists allow themselves to say that something is real and not a fluke, the same standard that certified the Higgs boson. The gap between the two ways of measuring the universe has now crossed that line. In the cold language of statistics, the disagreement is not an accident. It is a genuine feature of the data. Now feel the shape of what has happened here, because this is the emotional centre of the whole story. The scientists went looking for their own mistake. They wanted to find it. A mistake was the outcome that would let everyone relax, that would keep the universe familiar and the textbooks correct. They pulled the ladder apart rung by rung. They built an entirely separate ladder out of different stars. They refined the ancient light, and at every step they were, in effect, hoping to catch themselves in an error. And they could not. The harder they looked for the flaw that would make the problem go away, the more certain it became that there was no such flaw. One by one, the comfortable explanations were tested and set aside, and the disagreement was left standing, sharper and more significant than before. That is a strange and lonely feeling to sit with, and it is worth sitting with slowly in the dark without rushing to resolve it. We are so used to the idea that when something does not add up, the fault is ours. We miscounted. We misread the instrument. We forgot to carry a number somewhere. That assumption is usually correct, and it is the humble, healthy default of all good science. But here, that default has been tested to its limit and has quietly failed. The measurements are sound, the methods are independent, the people are careful, and they have been trying for years to prove themselves wrong, and still the two numbers will not meet, which forces open a possibility that is far harder to hold than a simple error, the possibility that nothing is broken in the measurements at all, and that the disagreement is trying to tell us something true about the universe that we do not yet know how to hear. It is worth walking slowly through the suspects, because the sheer thoroughness of the search is the whole reason the result is so unsettling. Take dust, for instance. Space is not perfectly empty, and clouds of fine dust drifting between the stars can dim and redden the light passing through them, exactly the way a distant streetlight looks fainter and warmer through haze. If the astronomers had failed to account for dust properly, a supernova might look dimmer, and therefore farther than it truly was, throwing off the top of the ladder. So they modelled the dust, measured it, corrected for it, and tested what would happen if they had gotten it wrong. The number held. Take the chemistry of the stars, what astronomers call metallicity, the proportion of heavier elements in a galaxy. It was possible that Cepheids in galaxies richer or poorer in these elements pulsed a little differently, subtly biasing their distances. So they measured that too and folded in the correction. The number held. Take the very bottom of the ladder, the parallaxes that anchor everything above them. If the geometric distances to the nearby Cepheids were even slightly off, that error would climb all the way up the structure. But the Gaia spacecraft has measured those parallaxes to a precision no earlier generation could have imagined, tightening the bottom rung to a firmness that leaves almost no room for hidden bias. One after another, the suspected sources of error were hauled in, examined, and released. Each correction was real, each was worth doing, and not one of them brought the ladder's number down to meet the ancient light. The 73 would not fall. The one genuinely serious challenge from within came, as we touched on, from the tip of the red giant branch, and it deserves real weight, because it is the strongest reason for humility in the whole story. When Wendy Friedman and her colleagues rebuilt the local measurement using those bright red giants instead of Cepheids and landed near 69 or 70, They were not being careless or contrarian. They were doing exactly what good science demands, checking a critical result by a completely independent path. Their intermediate number is a real result, and it has to be taken seriously. It is the reason no honest account can call the tension a clean, settled, two-sided fact. There is a genuine, unresolved argument inside the local camp about the last decimal places. But here is the crucial point that survives even that argument. Even the lower red giant number does not reach down to 67.5. It sits closer to the ladder than to the ancient light. Whichever local method you trust most, the early universe remains the low outlier, alone at the bottom, and nothing local will come all the way down to keep it company. And all the while, the significance kept climbing, which is the coldest part of the entire account. When two measurements disagree, statisticians can put a number on how seriously to take the gap, and that number is counted in sigma. Early on, the disagreement stood at around 2 or 3 sigma, the kind of tension that sometimes melts away with more data, an itch that might turn out to be nothing. But the data did not make it melt. As both sides sharpened their tools, the significance rose, past 4 sigma, and then past 5. 5 sigma is the line physics draws for a genuine discovery, the same standard used to certify the Higgs boson, the point where the odds of a fluke fall below 1 in 3 million. The disagreement between the two ways of measuring the universe has crossed that line and kept going. By the field's own strictest rule, this is not noise, it is real. Now let the human weight of this settle over you slowly, because it is the quiet heart of the whole story. Picture the scientists at their desks through all those years, running the checks, hunting the flaw, wanting more than anything to find it. A found error would have been a career-making relief. It would have let everyone exhale and kept the universe exactly as familiar and comprehensible as it had always felt. They went looking for their own mistake with real hope of catching it, and the universe would not grant them the mercy. Every door they opened in search of the error led only to another sound measurement. The comfort of it is only an error was taken from them, one careful check at a time, until what remained was the far harder thing to hold. Not that the scientists are wrong, but that the universe itself is out of step with our best description of it, and, as far as anyone can now tell, has been out of step all along. But there was still one more test to come, the biggest and most decisive of them all, because the single most suspected weakness in the ladder, the one soft spot where a hidden error might still be lurking, had to do with the crowded fields of stars where the Cepheids live. And to check that final suspect, astronomers needed an instrument sharper than any that had ever flown. They needed the most powerful telescope ever built, and when it turned its eye on the problem, it did not bring the relief everyone was hoping for. The last hiding place for a mistake had a name, and the name was crowding. Cepheid stars live in the busy, crowded arms of spiral galaxies, surrounded by countless other stars packed close together. When you photograph one of these pulsing stars from very far away, the light of its neighbours can blend into it, spilling into the same little patch of your image. If some of that neighbouring light gets counted as part of the Cepheid, the star looks brighter than it truly is, and a star that looks too bright looks too close, which would throw off the whole ladder. This was the most serious remaining suspicion. What if the Cepheids in distant galaxies were being subtly contaminated by crowding, making them appear brighter and nearer than they really were, and secretly inflating the local number up towards 73? For years this was the objection with real teeth, the crack in the rung that might still at last explain everything and let the tension dissolve. There was only one way to settle it. You needed an eye sharp enough to see those crowded Cepheids cleanly, to separate each pulsing star from its neighbours, to strip the crowding away and measure the true brightness with nothing spilling in. And in the last few years, humanity finally built that eye. The James Webb Space Telescope, the largest and most powerful telescope ever sent into space, sees the universe in infrared light with a sharpness far beyond anything before it. Its great segmented mirror can resolve details that were hopelessly blurred to earlier instruments. If crowding was the hidden flaw poisoning the Cepheid measurements, James Webb would expose it. It would resolve the crowded fields, peel the neighbours away from the target stars, and the inflated brightness would deflate, and the local number would finally begin its long-awaited slide down towards 67, and the century-old picture of the cosmos would be saved. Let yourself ride along with that light for a moment, the way the astronomers must have imagined it. Picture the glow of a single Cepheid. leaving its home in a distant galaxy tens of millions of years ago, crossing the emptiness in a thin thread of infrared, and arriving at last at the golden mirror of James Webb, folded open in the cold and the dark far beyond the moon. In the older, gentler eye of the Hubble telescope, that star had always been a soft smudge, its light mingled with the crowd around it. Now, as James Webb gathers the same starlight and focuses it with its far sharper vision, the crowd pulls apart. The neighbouring stars separate out into their own distinct points. The target Cepheid stands alone at last, clean and unblended, its true brightness laid bare for the first time. This was the moment of truth, the test that would either heal the tension or seal it. And everyone leaned in to see how far the number would fall. It did not fall. When the astronomers, led by the same team that had long championed the local measurement, compared the crowd-free James Webb distances to the older Hubble distances for the very same stars, the two agreed almost perfectly. The difference between them came out to within a whisker of zero, a mismatch smaller than the width of the uncertainties. The crowding, the last great suspect, had not been fooling anyone. The Cepheids had been measured correctly all along, and the hypothesis that crowding could explain the Hubble tension was not just weakened, it was rejected with crushing finality at a confidence of more than 8 sigma, an even higher certainty than the tension itself. The sharpest eye ever built had looked directly at the most suspected flaw in the entire ladder, and found the ladder sound. Feel the quiet enormity of that result. The whole point of building a sharper telescope had been, in the hopes of many, to make the problem go away. Instead, James Webb did the opposite. It removed the single most plausible escape route. Before, you could always tell yourself that maybe the crowding was doing it, that maybe the newest instrument would reveal the error and restore the old comfortable universe. After James Webb, that hope was gone. The ladder is solid, rung by rung, all the way up. Parallax at the bottom, holding firm. The Cepheids in the middle confirmed by the sharpest vision we possess. The supernovae at the top carrying the measurement into the deep cosmos. There is no loose rung. There is no smudge of crowding secretly inflating the answer. The ladder gives 73, and it gives 73 honestly. And on the other side of the divide, the early universe measurement has only grown more secure as well. It is not as though one lonely instrument read the ancient light and everyone simply trusted it. Other observatories have mapped the cosmic microwave background from high, dry mountain tops, tracing the same frozen ring of primordial sound with independent instruments and independent teams. The most recent of these efforts, completing its final maps, has reaffirmed the early universe value, landing squarely near 67, right where the Planck spacecraft had placed it. So the early road, too, has been walked again by fresh feet, and it leads to the same low number. Both sides have been checked and rechecked, and neither will move. So here we are, standing at the place the whole story has been carrying us toward. Both roads are sound. The ladder is confirmed all the way up by the most powerful telescope ever built. The early universe reading is confirmed by multiple independent maps of the oldest light. The measurements are not fuzzy, they are sharp. The people are not careless. They have spent a decade trying to prove themselves wrong, and still the two numbers will not shake hands. 73 from the nearby universe, 67.5 from the dawn of time, a 9% crack that every new instrument, every new check, only carves deeper into the foundation. It is worth understanding just why the James Webb Telescope was the right instrument for this particular question, because it was not simply a matter of being newer or larger. The problem of crowding is fundamentally a problem of sharpness. When two stars sit close together on the sky, a telescope with limited resolution blurs them into a single blob, and their light gets counted together. The larger and more perfect a telescope's mirror, the finer the detail it can separate, and the more cleanly it can tell one star from its neighbour. James Webb carries a mirror far larger than the aging telescope that had done the earlier work, and it observes in infrared light the longer wavelengths that slip more easily through the dust of distant galaxies and reveal the cool, crowded stellar fields where Cepheids live. It was, in a very real sense, purpose-built to look at exactly the kind of scene where a crowding error could hide and to strip that crowding away. The test itself was elegant in its logic. There is a particular nearby galaxy whose distance is known with unusual confidence, measured by a method even more direct than Cepheids, using the motion of gas swirling around the black hole at its centre. This galaxy serves as an anchor, a fixed point everyone can agree on. The astronomers pointed James Webb at the Cepheids in that anchor galaxy, and in several other galaxies that had also hosted Type Ia supernovae, and they measured more than 1,000 of these pulsing stars all over again, this time with Webb's superior sharpness. Then they compared star by star the distances Webb gave against the distances the older telescope had given for the very same stars. If crowding had been corrupting the older measurements, the two sets of distances would diverge, and the divergence would grow with distance, exactly the signature the skeptics had predicted. There was no divergence. The difference between the old distances and the new, crowd-free ones came out to within 1/100th of a unit of brightness, a mismatch so small it was consistent with zero. The Cepheids had been measured correctly all along, and the astronomers were able to state the result in the cold, precise language of statistics. The idea that crowding explains the Hubble tension was rejected at more than 8 sigma. Sit with that figure for a moment, because it is quietly enormous in its own right, larger even than the significance of the tension itself. The one remaining hope for a mundane explanation, the last loose rung anyone could point to, was not merely weakened. It was ruled out with more confidence than almost anything else in the whole affair. Let yourself ride along with that light one more time, because it is worth feeling rather than only knowing. The glow of a single Cepheid leaves its home galaxy tens of millions of years ago, a thin thread of infrared crossing the dark. In the older, gentler eye of the earlier telescope, that thread had always arrived smeared into the light of its crowded neighbours, a soft and slightly uncertain smudge. Now the same thread of light falls onto the great golden mirror of James Webb, folded open in the cold far beyond the moon, and this time the crowd pulls apart. The neighbouring stars resolve into their own separate points. The target Cepheid stands alone at last, clean and unblended, its true brightness finally laid bare, and its distance, measured cleanly for the very first time, matches the old distance almost exactly. The rung was sound all along, the ladder holds, and the escape route everyone had been quietly counting on clicks softly shut. I keep saying the ladder holds, and I want to be sure the full meaning of that lands, because it is the hinge of the entire night. Every rung has now been tested by the harshest scrutiny we can bring to bear. Parallax at the bottom, anchored by a spacecraft measuring the wobble of stars to millionths of an arc-second. The Cepheids in the middle, confirmed by the sharpest telescope ever flown. The exploding stars at the top calibrated and cross-checked and standardized one explosion at a time. There is no soft spot left, no smudge of crowding, no uncorrected dust, no miscalibrated rung to blame. The ladder gives 73, and it gives 73 honestly, all the way up. And on the far side of the divide, the ancient light gives 67.5, confirmed now by more than one independent map of the early universe, including the most recent readings from a great telescope perched high in the mountains, which traced the same frozen sound and landed in the same low place. Both roads are sound, both roads are confirmed, and still they will not meet. Which leaves us finally with the possibility that the astronomers spent 10 years trying to avoid. If it is not a mistake in the ladder, and it is not a mistake in the ancient light, and it is not a fluke of statistics, then perhaps it is not a mistake at all. Perhaps the two numbers are both correct, and if both numbers are correct, then the fault lies not in our measurements, but in the story we tell to connect them, the model of the universe itself. Perhaps the reason the early universe and the nearby universe disagree about the expansion rate is that something happened in between, something our standard picture of the cosmos does not yet include. To understand how new physics could rescue both numbers at once, you have to see exactly where the two measurements part ways. The local ladder measures the expansion rate directly, here and now, by watching nearby galaxies recede. It reads the universe as it actually is today. The early universe method is different. It does not measure today's expansion directly. It measures the size of that frozen sound ruler in the infant cosmos, and then it uses the standard model of the universe, the accepted account of everything that has happened since, to calculate forward and predict what the expansion rate should be now. In other words, the early number is not purely an observation. It is an observation of the infant universe, plus a theory of everything that came afterward. And that means there are two ways it could be wrong without any instrument being at fault. The ruler itself could be a slightly different size than we think, or the story we tell about what happened between then and now could be missing a chapter. Most of the leading ideas take aim at that frozen ruler, the sound horizon. Here is the clever logic. If some extra ingredient existed in the very early universe, before the fog cleared, it could have changed how fast the cosmos was expanding in those first hundreds of thousands of years. That would change how far the primordial sound waves managed to travel before they froze, which would make the ruler slightly smaller than the standard model assumes. And a smaller ruler, seen at the same apparent size on the sky, would imply a faster expansion, nudging the early universe number up from 67 towards 73, closing the gap. So a whole family of proposals asks the same question. What could have been present in the first moments of the universe that we have not accounted for? One leading candidate is called early dark energy. The idea is that a temporary burst of a dark energy-like substance flared into existence in the early universe, did its work of subtly speeding up the expansion and shrinking the sound ruler, and then faded away before it could disturb anything else. It is an elegant fix, and in the right amount it can pull the two numbers together. But it comes at a price. When you add early dark energy to make the expansion rate agree, it tends to throw off other measurements, particularly the way matter is clumped into galaxies and clusters across the sky. Solve one tension, and you risk aggravating another. The universe, it seems, does not give up its secrets cheaply, and every patch you sew onto the model tugs a different seam loose. There are other candidates, and it is worth hearing them because the sheer variety of them tells you how genuinely open this question is. Some propose extra kinds of ghostly, fast-moving particles in the early universe, a form of dark radiation that would also change the early expansion. Some propose that dark energy is not constant at all, but slowly changing its strength over cosmic time, an idea that recent large surveys of galaxies have hinted at, and which would alter the calculation from the early universe to now. Some propose faint magnetic fields threaded through the primordial plasma, subtly changing how the first atoms formed and how the sound ruler set. Some ask whether we happen to sit inside an unusually empty bubble of space, a local void so that our nearby measurements of expansion read a little fast compared to the true cosmic average, though most careful studies find the bubble would have to be improbably large and deep to do the job. Each of these is a serious idea, pursued by serious people, and none of them has yet emerged as the clear answer. I want to be honest and careful here, in the way this channel always tries to be, because it would be easy to overstate this. Nobody has solved the Hubble tension. There is no confirmed new particle, no proven early dark energy, no established new force. These are candidates, hypotheses, directions people are searching, and every one of them still has problems. It is entirely possible that the answer, when it comes, will be something no one has thought of yet. It is even still possible, though it looks less likely every year, that some deep shared systematic error hides in both measurements in a way we have not yet imagined, and that a careful reanalysis will one day bring the numbers gently back together. A minority of thoughtful researchers still hold that door open, and intellectual honesty requires that we hold it open too, if only by a crack. But the direction the field is leaning is unmistakable, and it is a remarkable thing to say out loud. More and more cosmologists are treating the Hubble tension not as an embarrassment to be explained away, but as a genuine signpost, a place where the universe is quietly telling us that our standard model for all its sweeping successes is incomplete. That model has passed test after test for decades. It correctly predicts the amounts of the lightest elements forged in the first minutes. It correctly describes the pattern of the ancient light. It has been one of the most successful theories in the history of science. And yet here, in the simple question of how fast the universe is expanding, it may have finally hit its edge, the place where a new piece of physics is waiting to be found. Before we go further into the exotic ideas, it is worth being very clear about the strange logic that makes the early universe number a theory as much as a measurement, because this is where any solution has to do its work. When the Planck spacecraft reads the ancient light, what it directly sees is the pattern of warm and cool patches, and from that it measures the true physical size of the sound horizon ruler with great confidence. That part is close to pure observation. But to turn that ruler into a present-day expansion rate, you have to assume you already know everything important that happened to the universe in between, all 13 billion years of it. You have to feed the ruler through the standard model of cosmology and let it calculate forward. So the early number is really a statement of the form. If the universe contains exactly the ingredients we think it does, and nothing more, then the expansion rate today must be 67.5. Change the list of ingredients, especially in the first moments, and that prediction can shift. This is the seam that every proposed solution tries to pry open. The most popular attempts, as we said, try to shrink the sound horizon by adding something to the early universe. Early dark energy is the leading candidate, a brief pulse of a repulsive energy that flares just before the fog clears and then vanishes. Give the early universe that extra push, and the sound waves freeze at a slightly smaller size, and a smaller ruler implies a faster present-day expansion, sliding the early number up towards 73. On paper, it works. But nature keeps the books carefully, and when you add early dark energy in just the right amount to fix the expansion rate, it tends to disturb the delicate pattern of how galaxies are clustered across the sky, opening a fresh disagreement even as it soothes the first one. This is the recurring frustration of the whole enterprise. The model is so tightly interlocked that a patch sewn onto one corner pulls a thread loose in another. The other ideas each carry the same double edge. Perhaps there were extra species of ghostly fast-moving particles in the young cosmos, changing its early expansion. Perhaps dark energy is not a fixed constant but slowly shifting over billions of years, an idea that recent enormous galaxy surveys have hinted might be true, which would quietly change the whole calculation. Perhaps faint magnetic fields were threaded through the primordial plasma, nudging how the first atoms formed. Perhaps we simply live inside an unusually empty pocket of space that makes our local measurements read a little fast, though the pocket required looks improbably large and deep. Each idea can ease the tension. None can do so without a cost somewhere else, and none has yet risen clearly above the rest. The universe is being coy, offering many possible answers and confirming none of them. What gives me the most hope is not any single one of these ideas, but the fact that astronomers are no longer leaning on just two roads. They are building entirely new ones, independent of both the ladder and the ancient light. When two neutron stars collided and were caught by gravitational wave detectors, the ripples in space they sent out carried, encoded within them, a direct measure of the distance to the collision, with no ladder and no Cepheids required at all. Astronomers call these events standard sirens, and each one is a fresh, independent reading of the expansion rate. There are other new roads too. Some teams measure the tiny time delays as light from a single distant source bends around a massive galaxy and takes several paths to reach us, and those delays reveal the scale of the universe. Others watch the precise motion of gas around distant black holes, or lean on a different class of exploding stars entirely. Each of these methods is still young, its uncertainty is still wide, but as they mature, they will settle, independently, onto either the 73 or the 67, and in doing so they will tell us which road was right, or whether the truth sits somewhere stranger in between. That, in the end, is how this will be settled. Not by argument, but by an accumulation of new and independent measurements, until the answer becomes undeniable. It is entirely possible that within a few years the gravitational wave sirens and the lensing delays and the rest will pile up on one side and end the debate. It is also possible that they will scatter in a way nobody expects and deepen the mystery further. And it is still possible, though it looks less likely with each passing year, that a subtle shared error hides in the measurements after all, and that the whole tension will one day dissolve as quietly as it first appeared. Honesty requires holding all of these open. But the direction of travel is unmistakable, and it points towards something new. There is a quiet thrill hidden inside that discomfort, and it is the feeling this channel exists to share. Every so often in the history of science, a small stubborn discrepancy that everyone wanted to dismiss turned out to be a doorway. A tiny wobble in the orbit of a planet became the theory of general relativity. A faint hiss in a radio antenna became the discovery of the ancient light we have been discussing all night. A small, nagging disagreement that refuses to go away has a habit in this field of becoming the next revolution. The Hubble tension might be exactly that kind of discrepancy, a 9% crack that turns out to be a window. And to see what lies on the other side of it, we have to return one last time to the number we started with, and ask what it really means that the scale of the universe has stopped making sense. Think back to where we began, to that single modest number, the rate at which space is stretching, the master key that unlocks the size and age of everything. We said that if you change it, even slightly, all the great numbers shift beneath your feet. Now we can feel the full weight of that. When you read that the universe is 13.8 billion years old, or that the part we can see is some 93 billion light-years across, those figures are not carved into stone. They are calculated from the expansion rate. and the expansion rate is precisely the thing our two best methods cannot agree on. Depending on which number you trust, the 73 or the 67.5, the age of the universe shifts by hundreds of millions of years, and its size shifts with it. The textbooks give you a single tidy figure because a single figure is easier to hold, but underneath that tidy figure sits a 9% crack, running the whole length of the map, and the crack is real. This is what the title of tonight's exploration has been pointing toward the entire time. The more carefully scientists look into the scale of the universe, the less they understand it. And I want to be precise about what that sentence does and does not mean, because it is easy to misread. It does not mean that astronomers are incompetent, or that the science is collapsing, or that we know nothing. The opposite is true. We understand the universe well enough to have built two magnificent independent measuring systems, each accurate to about 1%, each a monument to a century of human patience. The strangeness is not that we know too little. The strangeness is that we now know enough, and measure well enough, to be certain that two correct-seeming answers cannot both be right, and to be unable, so far, to say why. It is the peculiar situation where more precision has produced not more clarity, but a deeper and sharper mystery. There is something almost humbling in the shape of it, and I mean humbling in the good way, the way that makes the world feel larger rather than smaller. For most of human history, we did not know the size of the universe at all. The stars were lanterns on a wall at unknown distances. Then, rung by patient rung, we learned to measure the unmeasurable. We stood on the honest triangles of parallax. We timed the pulses of stars using a law found by a woman working in silence at Harvard. We caught the whole cosmos in the act of expanding on a mountaintop in California. We read the frozen ringing of the newborn universe off the oldest light there is. Each of these was a genuine triumph, and when we finally laid our two greatest achievements side by side, expecting them to confirm each other, they refused to shake hands. The universe handed back two different answers, and in doing so it reminded us that it is still keeping secrets, even about something as basic as its own size. That refusal is not a failure, it is an invitation. Remember what small, stubborn discrepancies have done before in this science. The tiny wobble in a planet's orbit that would not go away became a new understanding of gravity and the shape of space and time. The faint static in a radio antenna that nobody could get rid of became the discovery of the ancient light itself, the very glow we now use to measure the early universe. Over and over, the little disagreement that everyone wished would vanish turned out to be the doorway to the next, deeper picture of reality. The 9% crack may be exactly this kind of doorway. Somewhere on the other side of it may be a new form of energy that flared in the first moments of time, or a new particle we have never caught, or a subtle rule about the early universe that no one has yet written down. We are standing at the crack, holding a lantern, looking in. And notice what has quietly happened to the two numbers over the course of this night. They began, in the first part, as a curiosity, an odd little mismatch between 73 and 67.5. But we have followed each of them all the way down to its roots, down through the rungs of the ladder to the geometry of a triangle and the pulse of a distant star, down through the ancient light to the ringing of the infant cosmos. And now those two numbers are not a curiosity anymore. They are the two most carefully built measurements humanity has ever made of its own home, standing a hand's breadth apart and refusing to meet. Two numbers that will not shake hands. And the space between them, that small stubborn gap, has become one of the most important empty spaces in all of science, because whatever fills it will change the story we tell about the universe. So the next time you see one of those clean, confident diagrams of the cosmos, the ones with the age printed neatly in the corner and the size labelled along the edge, you will know the quieter truth hiding behind the tidy numbers. You will know that those figures rest on a rate of expansion that two flawless-seeming methods measure differently. You will know that our newest and most powerful telescope was sent to heal the disagreement, and instead made it deeper. You will know that some of the most careful people alive have spent a decade trying to prove themselves wrong and have not managed it. And you will know that this is not a reason for worry, but a reason to keep looking, because the universe has just told us in the plainest way it can that our map is not yet finished. There is a particular kind of peace in that, if you let yourself feel it. We do not live in a solved universe, a closed book with all its pages read. We live in one that is still revealing itself, still holding a mystery at the very heart of its scale, still large enough to surprise the species that has spent 100 years learning to measure it. The two numbers will meet someday, Someone, perhaps someone alive right now, perhaps someone drifting towards sleep to a voice like this one, will find the missing piece that reconciles them, and when they do, our picture of everything will quietly grow larger and truer than it was before. Until then, the crack remains, patient and open, a 9% reminder that the cosmos is deeper than our certainty. There is a particular reason this mystery feels different from the fears people usually attach to the sky, and it is worth naming before we let the night settle in fully. Most of what unsettles people about the universe is a matter of size or violence, the enormous distances, the exploding stars, the black holes waiting in the dark. But this is not that kind of unease. Nothing here threatens you. The universe is not doing anything to us that it has not been doing gently for 13 billion years. What has changed is only our knowledge of it, or rather our sudden clear view of the very edge of our knowledge. We have not uncovered a danger. We have uncovered a boundary, a place where our understanding, for all its reach, quietly runs out. And there is something almost tender about arriving at that boundary honestly, with our finest instruments in hand, and being able to say, plainly and without shame, that we do not yet know. Think about how rare and how recent this position is. For nearly all of human history, no one had any idea how far away the stars were, let alone the galaxies, let alone the edge of the observable universe. The size of the cosmos was not even a question you could ask with any hope of an answer. And then, in a single century, a deaf woman at a desk, 2 men in a cold dome, a spacecraft reading the oldest light, and a golden mirror beyond the moon carried us from complete ignorance to a measurement good to about 1%. That is an astonishing climb. The fact that at the very top of it we find 2 answers, instead of 1, is not a mark of failure. It is a mark of how far we have come, that we can now measure the universe well enough to notice that it is subtly, genuinely stranger than our simplest picture of it allows. And notice, one last time, what has happened to the 2 numbers over the course of this night, because it is the whole arc in miniature. They began as an odd little mismatch, 73 against 67.5, the sort of thing you might expect to heal on its own. We followed each of them all the way down to its roots, down the rungs of the ladder to the geometry of a triangle and the pulse of a distant star, down through the ancient light to the ringing of the newborn cosmos. And now those 2 numbers are not a curiosity anymore. They are the 2 most carefully built measurements our species has ever made of the size of its own home, standing a hand's breadth apart and refusing to meet. 2 numbers that will not shake hands. The space between them, that small stubborn gap, has quietly become one of the most important empty spaces in all of science, because whatever finally fills it will reshape the story we tell about everything. So the next time you see one of those clean, confident diagrams of the cosmos, the ones with the age printed neatly in the corner and the width labelled along the edge, you will know the quieter truth hiding behind the tidy figures. You will know that those numbers rest on a rate of expansion that 2 flawless-seeming methods measure differently. You will know that the sharpest telescope ever built was sent to heal the disagreement and only carved it deeper. You will know that some of the most careful people alive spent a decade trying to prove themselves wrong and could not manage it. And you will know that this is not a reason for worry, but a reason to keep watching the sky, because the universe has just told us, in the plainest language it has, that our map is not finished being drawn. For now, there is nothing you need to solve and nothing you need to fear. There is only an enormous, quiet universe, expanding gently in every direction, at a rate we have measured twice and cannot yet agree on, carrying us and our questions along with it into the dark. Rest easy under that unfinished sky. The 2 numbers will keep their standoff through the night, and the ancient light will keep arriving, and the exploding stars will keep marking out the distances, whether or not we are awake to watch them. And somewhere out there in the space between 73 and 67, the next great secret of the universe is waiting, in no hurry at all for us to be ready to hear it.